I want to do some calculations in quantum mechanics to do a simple example of probabilities of measurement outcomes for an electron in a particular quantum state. So just to review some ideas, the quantum state vector for an electron is a two-component object, and we're expressing these, for simplicity, in the bases of states corresponding to measurements of the spin of the electron along the z-axis. So the plus z state, where you'd measure the electron spin to be plus hbar over 2 along the z-axis, would be 1, 0 in our basis, and the minus z state would be 0, 1 in our basis. These aren't like x hat, y hat states in space. These are the states of a quantum space that just happens to be two-dimensional, two possible outcomes for any particular spin measurement you might make. We've talked about this before. So, okay, we're going to look in particular, I guess I should comment just for the record, other possible spin measurements we could make. If I measured the spin along the z-axis, those are the two answers I gave originally. If I measure the spin along the x-axis, the plus x quantum state in this basis is represented as 1 over square root of 2 in the first component and 1 over square root of 2 in the second. The minus x state is 1 over square root of 2 and minus 1 over the square root of 2. You can check that those are orthogonal, all this business. And again, the y states 1 over square root of 2 in the first component and I, square root of minus 1, over square root of 2 in the second component. And the minus y state is 1 over square root of 2 and minus I over square root of 2. These are standard conventions for the basis states and for the measurements along these different axes. You can do it in different ways. This is the standard way we do it in the SZ basis. So okay, with that in place, our example, everything we do is going to be for this quantum state psi. This is a ket vector psi, column vector, that is given by 4/5 I in the first component and 9/25 minus 12/25 I in the second component. It seems kind of like a weird combination, but in a previous example, we figured out that this was the normalized vector with those proportions, the normalized state vector with those proportions. Remember, normalized just means that the ket, the bracket of this state with itself, gives you 1. That you've got, if you start in state psi, you've got a complete probability of measuring yourself in state psi. All right, so with that in place, I want to just do a few examples. What's the probability if I start with a bunch of electrons in state psi? What's the probability that I'll measure them in state Sz equals plus hbar over 2? If I measure the z component of spin, that I'll get the positive hbar over 2 result. All right, well, to do that, every time I ask a question, a measurement question in quantum mechanics, I have to put together kets and bras in an appropriate way. And so in particular, if I start in state psi, I always have the ket psi as my starting point for that state. Then, if I want to say, what's the probability be in this particular quantum state to be measured there, I look at what that quantum state vector is that I'm measuring it in. I have to take the conjugate transpose to get the corresponding bra, but I'm going to say, okay, here's my initial state. Maybe I can label it this way. Here's my initial state, and here is my measured state. So the ket tells me where I start, the bra asks a question. And then, to get a probability, I want probability here, I have to do one more step. I have to take the absolute value squared, the complex absolute value squared of that quantity, of that bracket of plus z with psi. All right, let's see how this works out. That means that this is, here we go, this is equal to the absolute square of the plus c bra is just the conjugate transpose of this. That means it's 1, 0, times my ket vector down here. Why did I give myself a ket vector that was such a pain to write? 9/25 minus 12/25 I and 20 I up here. Absolute square of that product. Hey, I can do that. Multiplying this out, that's equal to the absolute square of 1 times, oh, sorry, this isn't 20, this is 4/5. Thank you, the previous version. 1 times 4/5 I plus 0 times 9/25 minus 12/25 I. That's small because I don't care because it's multiplied by 0. Well, what is this? This is 0, and this is 4/5 I. Now, the fun part there is the absolute square of something. You can think of it as just being 4/5 I times 4/5 I complex conjugate, or in other words, minus 4/5 I. That'll be 16/25 I times minus I is plus 1. 16/25 is 64%. So I've got a 64% chance in this case that I would measure this to have SZ equals plus h bar over 2. Just to check, let me ask, what if I want to measure SZ equals minus h bar over 2? If I were to measure that instead, and what's the probability of measuring that? Again, I construct a bracket to ask the question. I say I start in state psi. The minus h bar over 2 z spin state is called minus z. So I ask a question by hitting it with the minus z bra, and then that bracket's absolute square is the probability. That's the probability I'm asking for, the probability here. And so again, I can do the same calculation. This is going to be equal to the absolute square of now 0, 1 times 4/5 I, 9/25 minus 12/25 I, absolute square, which 0 times that, 1 times that means it's just going to be 9/25 minus 12/25 I, absolute square. And as usual for complex numbers, I can either evaluate this by taking this times its own complex conjugate to find the absolute square, or I can switch it around the other way, and I can just think of this as a Pythagorean theorem thing, real part squared plus imaginary part squared. So this is equal to, because that's what we'll get to in the end if we multiply by complex conjugate anyway, this is going to be 9/25 squared, that's the real part, plus minus 12/25 squared. That's the imaginary part. Don't square the I, they both have to be positive in the end. What is that? That's 81 over 625 plus 144 over 625. When I multiply that out, or when I add that up, that is 225 over 625, or what is that? 9/25 is my, I forgot my, 9/25 is this, is what it comes out to, or 36%. So I have a 36% chance of measuring the SZ to be minus h bar over 2. And of course, it's good news that if I add 64%, that equals 100%. It had to add up to total probability 1, or else this wouldn't have been a good story at all. So that's that's how I ask a question about this system. I take it, I have my initial state. The bra asks a question, and I take the absolute squared to find the probability. And let me do one more example, just since we're working with this. Let's do one more example. Let's ask the question, what if Sx equals plus h bar over 2? How do I ask that question? Well, I do the same thing. I say, I'm starting in state psi, so I start with that ket. I'm asking a question of being in the plus x state. So I put the plus x bra in, that's the question I'm asking, and then for a probability, once I'm doing the measurement, I take the absolute square to do my measurement and find an answer. Oh, wow, the sun just came out. It's getting very glary. I apologize. Probably a good time to cut this short. I'll do this example though. So this will equal, let's see, 1 over square root of 2, 1 over square root of 2 times this ugly thing, 4/5 I, and then 9/25 I minus 12/25 I, absolute square, and that equals, let's see, 1 over square root of 2 times this, plus 1 over square root of 2 times this. I'll be a little sneaky here and just factor that out. 1 over square root of 2 times 4/5 I plus 9/25. That wasn't supposed to be an I. one of you in the video should have yelled at me. 9/25 minus 12/25 I, absolute square. And then I'm going to group the i's together. Let's see, 4/5 is the same as 20. Oh, that's an invisible. We're not going to do the orange. Never mind about the orange. 4/5 is the same as 20 over 25. So this equals the absolute square of 1 over square root of 2 times 9/25 minus 8/25 I. The fact that it's times I means these don't cancel out. So, because 20 minus 12 is 8. And when I multiply that out, that's the same as 1/2 times, again, the magnitude of this is going to be real part squared plus imaginary part squared. The 1/2 is just 1 over square root of 2 squared, which I factored out. And so what do I have? 81 over 625 plus negative 8 squared is 64 over 625. That's going to be putting, you can check that math on your own if you really want to, but that's putting it all together. When I add that up, what do I get? 2 times 625 is 1250 in the denominator, and that's 145. Yeah, it looks like it. 145 over 1250. I worked that out earlier. Let me just glance at what I got rather than embarrassing myself in front of you. All right, that's 29 over 250, or 0.116, 11.6%. So we're relatively unlikely to measure this one to be in the plus SX state. Now, if I wanted to ask the question about being in the minus SX state, minus h bar over 2, I'd need to do the same thing. I'd take the start in state psi. I'm asking the question about being in the minus x state, and then the probability is the square of that, the absolute square of that. But it turns out this would be a great way to do a double check to make sure I can double check the things add up to 100%. If I'm in a hurry, which I am, I can just say this has to be the rest of the probability. If there are only two states, and it's got 11.6% chance of being over there, then this has to equal the rest. What will that be? 100% minus 11.6% is going to be 88.4%. And if you want a little homework practice, you can do this calculation and verify that you get 88.4% as the result. Let me do one more thing to, now that we've talked about these probabilities, I want to talk about one more concept, just to share it with you. The one more concept I want to touch on is the idea of an expectation value. And that is, I've told you what the two probabilities are for each one of these, but it could be useful to know what's the average. If I had 1,000,000 of these electrons in state psi, what would be the average spin along the z component that I would find? The expectation value is really simple. I just say the expectation value is the average value. I take the probability of each outcome, multiply it by the number I'd get. So the expectation value for SZ, for example, is the probability of h bar over 2 is 64%, so I'll say 0.64 times h bar over 2 plus the probability of the minus case, that was 36%, so 0.36 times minus h bar over 2. Probability of this outcome is added to probability of that outcome. It's just, that's averages in probability, and that comes out to be, let's see, 64 minus 36, that would be 34, 28, 0.28 times h bar over 2, or 0.14 h bar, or 0.14 h bar. So I won't work out exact numbers, but that gives me an idea that if I measure the spin along the z-axis of a bunch of copies of this system, I'll get 0.14 times h bar. It's going to be pretty close to 0 in the middle, but it's going to be more positive than negative. That'll be my average. What about Sx? My expectation value for Sx, same thing. I take the probability of the first outcome, 0.116, that's my 11.6%, times h bar over 2, plus the probability of the second outcome, 0.884 times minus h bar over 2. And the minus means these are going to cancel out a bit more. They'll cancel out again. And let's see, 768, negative 0.768 times h bar over 2, which I guess I can divide by 2, negative 0.384 h bar is my expectation value here. So this time I have something that's almost minus 0.5 h bar. It's pretty close to being all in the minus h bar over 2 direction. And that's what I'm looking for. That's how I find an expectation value based on these things. I could have done the same thing with sy, but this video is all pretty long. The only thing you have to remember is when you do the plus y bra, you've got to take the complex conjugate of those terms. Don't forget to make it 1 over square root of 2 minus 1 over square root of 2 in the bra. But same thing could work there. If you want to try it at home, I worked out that expectation value, and it's negative 0.283. Sy, expectation value is negative 0.283 h bar. So if you want to get some practice and see how you do, try to get that calculation. Try to find that sy. You'll see that you come up with that answer. I hope that gives you an idea about how quantum mechanics asks questions and provides probabilities for the answers.